Next, we'd like to look at the pressure that a gas exerts in a container. In this case, we'd like to look at a container that has flexible walls, perhaps a latex balloon. What are the forces on a container? Well, in a balloon, we have air pressure, air molecules on the outside pushing in. These arrows, these black arrows, here and here, and all around, are relatively equally spaced apart. They are the same throughout. Even though there are more arrows on the right balloon than there are on the left balloon, the amount of pressure is the same. The amount of arrows per surface area is relatively constant. The pressure is the same. So, suppose we had gas inside these. And so in this case, we have quite a few gas molecules inside the balloon. Well, clearly the pressure on the inside is much greater than the pressure on the outside, and so this container is going to grow. This would expand. So we have our little formula here. The pressure from the atmosphere is much less than the pressure inside the balloon. Here you'll see that the pressure inside the container equals the pressure outside the container. And so our little equation that would show that would be something like that. The pressure inside of the atmosphere is equal to the pressure inside the balloon. And at an elementary level, this balloon would stay the same size. This is happy, this is good, this is in equilibrium. The pressure on the inside is equal to the pressure on the outside. The volume will stay this size. In our next example, we have the same number of molecules, but now they're spread out more. The same number of molecules are spread out more, and so they cannot match. You'll notice that there are more arrows here than there are there. The pressure on the outside of the container is larger. The pressure on the outside of the container has not changed, but the number of molecules on the inside are now more spread out. Since they're more spread out, this is not going to be a good thing. The pressure from the atmosphere is greater than that in the balloon. This balloon is going to shrink. So the balloon on the left is going to expand because the pressure inside is greater. The balloon on the right is going to shrink because the pressure on the inside is too small. And in our middle, the pressure on the inside balances equally the pressure from the atmosphere. Now, I told you that this was a little bit elementary. There's one layer that we haven't considered. There's another force that we have to worry about, and that is the pressure from the expanding, stretching latex. The balloon itself is going to stretch and is going to want to relax, and so there's a little extra force. So in reality, we should be looking at that. So in our middle case here, the pressure inside the balloon is really a little bit bigger than the pressure from the atmosphere because it also has to fight the latex. The atmosphere and latex together are trying to collapse the balloon. The pressure inside the balloon has to fight that. It's a small factor for us to worry about. Now if we move to a rigid container, a container like a pressure cooker that has rigid walls, it cannot expand. We don't have to worry about that. The atmospheric pressure on the outside doesn't really matter what it is because as they collide, the walls can't flex. So it doesn't matter what the pressure on the outside is if the walls are strong enough. The pressure on the inside has nothing to do with the pressure on the outside, as long as the walls are strong enough to handle that. How will we measure pressure? There are many different people that measure pressure, and they use different units for different reasons. Some of the units are pascals, or PA, that's the standard metric unit. It's quite small though, and so the numbers that you use are quite large. So we'll use kilopascals. Millimeters of mercury and torr are often used in the weather industry, and atmospheres can be used in a whole variety of engineering applications. It will be important for us to decide to be able to convert between the two. So, using our factorial label method, 480 kilopascals is how many atmospheres? Might look something like this. 480 kilopascals balloons. Now, as it turns out, the numbers in the chart are all equal to each other. 1 atmosphere is the same as 760 torr, it's the same as 760 millimeters of mercury, same as 101.3 kilopascals, and 101,300 pascals. They are all the same value. And so 1 atmosphere is the same as 101.3 kilopascals. The units will cancel, and that will work out to be 4.74 atmospheres. So looking at our next example, 480 kilopascals is how many millimeters of mercury? Well, I'll do exactly the same thing, the same process. Use a slightly different color so we can see the difference. We're still going to use 101.3 kilopascals on the bottom, but now I'm looking for millimeters of mercury. There we go. Kilopascals cancels with kilopascals. 480 times 760, all divided by 101.3, 3,600 millimeters of mercury. Using the factor label method, it's quite straightforward. So here's a chance for you to try. Using the chart, knowing that each value is worth the same amount, so 1 atmosphere is the same as 760 millimeters of mercury, which is the same as 101.3 kilopascals. Please convert 3.2 atmospheres into torr. Please convert 945 millimeters of mercury into kilopascals. Please do not do question number 2 just yet. The instructor should pause. And so let's run through this. We would have 3.2 atmospheres. Atmospheres on the bottom, torr on the top. 1 atmosphere is the same as 760 torr. So 3.2 times 760 divided by 1. And that will work out to be 2,432. Along that same line, (945) times 101.3 divided by 760 millimeters of mercury cancel, and that will give you 126. Okay, could the instructor please press start on the individual response systems? Students, could you please complete the next question? 55,689 pascals is how many millimeters of mercury? Please do not include any decimals in your answer. 55,689 PA 101,300 PAs on the bottom, 760 millimeters of mercury on top. And that works out to 417.